Hello, my name is Juan Rivera. I'm a Helicycle owner-builder. I have one helicycle that's completed and flyable, another partially finished kit, and I'm working on another one for a local builder. What you're looking at here is the back of the upper and lower instrument panels and an interface chassis that ties everything together for a helicycle. Do not despair. Don't be alarmed. This is a lot more complex than you need to go with a stock helicycle. I've got a lot of extra little bells and whistles here that most people don't have and probably don't want. In the first part that I did, I showed you how I do my schematic diagram so I can keep track of all the wiring. You can kind of see why I need diagrams by looking at this. In this part, I'm going to talk about cable selection and a little bit about why you want shielded cables and how they work. And then I'm going to do another part dealing with connectors. So I don't claim to be an expert, but I do know enough to stay out of trouble. My background is in electronics and avionics. I was an aircraft mechanic for United Airlines for 5 years. I've worked on the U-2 for a couple years and been around aircraft most of my life in various capacities. So here we go. The type of shielded cable that I suggest that you use is generally referred to as M27500 aerospace cable. I think the best place to find it, the one that I use often, is eBay. You can find short chunks and order it to the length you want, or they may say here's a 25-foot section or 50 or whatever, and usually you can just plunk down and buy it using PayPal, and in a few days there comes your cable. The trick is there's a million different kinds of cables. How do you know what you're getting? So I'm going to get into that in the next few slides. M27500 is actually an obsolete term for this cable. That refers back to a military spec that was canceled years ago and has since been replaced by a non-government commercial cable standard called NEMA WC 27500. So that's the current spec, but still the cables are referred to as M27500. This type of cable is used for low voltage power and signal applications, and it's designed for commercial and military aircraft and other high performance vehicles. Over on the right you see the makeup of a typical cable. This happens to be shielded twisted pair. So you have two conductors in the middle which are twisted, and I'll explain all of that later, why you twist them. The conductors typically are copper, various strands of copper that go in the middle. They're always plated with something. The most sophisticated cables will be silver plated copper. The more common will be tin plated. Either one's fine. Around the conductors then is a shield, and the shield can be woven round wire, very, very small strands, or can be woven tape, as I will show you later. And then around the shield is the outer jacket that protects the whole thing, and both the insulation and the jacket can be of various materials. Common ones are Teflon and Tefzel, and I'll show you in the next couple slides how we're going to determine what exactly it is that you're looking at. Here's the part number breakdown for this type of cable, and it always follows this same format. So you have the M27500 at the beginning. Usually a dash number, although from this breakdown it looks like you could have a letter designation there which would refer to shield coverage and color coding. I've never seen that. The 20 in this case shows that the conductor size is 20 AWG, or American wire gauge. The SB, you'd look that up in a chart and you'd find out what the base wire spec is. And I'll show you 2 examples in a second. The 3 tells us that there are 3 conductors in this particular cable. The T, again, comes out of a table that will tell you what type of shield you have. And then the number designation at the end, you look that up in another table, it will tell you what the outer jacket material is made of. So now let's look at two samples that I actually have here in my shop. Okay, this first example is M27500-20RC2S06. So this decodes as follows. The 20 after the dash tells you it's 20 AWG interconductors. The RC, then you look that up in a table that leads you to another spec for the individual conductors. In this case, it's M22759/11 construction. When you look that up, you'll find out that yes, it's 20 AWG interconductors, and they are in fact silver-plated copper. So this is a very high-quality cable. You can tell by the silver plating. The insulation is PTFE. And then they go on to tell you that it's non-stick with a 0.010 nominal wall thickness. So you find out all this stuff when you drill down a little bit. The voltage rating is 600 volts, and the temperature rating is 200 C. The 2 then tells you that this is 2-conductor. The S says it's a single silver-coated copper round shield construction. So it's round, tiny strands all woven into a shield, and there's silver-plated copper again. So both the shield and the interconductors are silver-plated copper. So this is high-quality stuff. The outer jacket, the 06, then you look that up in a table, you find out it's PTFE extruded on tape, and it's white. Let's look at one more example. Okay, here's another one. Again, left to right. When we get to the 22, we see that it's 22 AWG again. The SD, then we look that up, and that takes us to a totally different spec for the conductor itself. In this case, it's M22759/11. This is 22 AWG tin-plated copper. Insulation is cross-linked modified ETFE. I'm not sure what that is. I think it's probably Tefcel, but you could look that up. Another voltage rating of 600 volts and another temperature rating of 200 C. The 3 tells us this is 3-conductor shielded cable. The T tells us it's a single tin-coated copper round shield. So again, it's made out of tiny round strands of tin-coated copper that are woven together into a shield. The outer jacket is PTFE extruded on tape, and it is also white, which is the most common color that you'll see. So those are 2 examples, and using that decoder in the second or third slide that I showed you, you'll be able to break down any 27500 part number that you see and figure out what exactly it is they're selling. So why do we want shielded twisted pair in the first place? Here I've made a simple little schematic showing the engine RPM sensor, which is a variable reluctance sensor, which consists of a coil of wire over a pole piece. And the pole piece is in close proximity to the flywheel in the engine, And that flywheel has holes bored into it at regular intervals. So every time a hole goes by, there's a discontinuity in the magnetic field that induces a voltage in that coil of wire. So if we take a snapshot and freeze everything in time at the peak of one of these pulses, so that the output wire at the top is at a plus voltage and the one at the bottom is minus, what you see is as you twist these twists is the plus and the minus wires reverse. And so you have a series of pluses and minuses all the way the whole long length of the wire. And the net result of that is all of these electric fields all cancel each other out. That's the whole purpose of twists. And so the electric field that would be radiated from these conductors basically cancels itself out. And the inverse of that is any noisy signal trying to get into the cable conductors and couple in there and induce a noisy signal on top of the one that we're trying to transport through that cable, will run into the same situation. The field reverses so many times because of the twist that it cancels itself out. And so that's how we deal with the let me think about this, it gets a little confusing. So we have a magnetic field that can go right through the shield. It's not stopped by the shield, but the twists deal with a magnetic field. The electric field will not be able to get through the shielding. And so the signals that we're trying to get rid of or keep inside the cable are called electromagnetic radiation. And so there's two components, the electric field and the magnetic field, and the twists and the shield deal with those two separately. So that's why we do that. Now the idea behind the shielding is it's just an extension of the enclosure, for example. So say that enclosure is your VHF transceiver, and the cable we're looking at is the microphone input. That's a very low level signal coming from your microphone, and we don't want any noise induced onto your audio. And so the sensitive circuitry inside the transceiver is all sealed up inside of a metal enclosure, and then coming out the back connector, that cable then is simply an extension of the shielding around the enclosure, and it would go all the way out to the connector that your microphone hooks up to, for example. In this drawing I'm showing both ends of the shield connected. Typically you float the far end, and that's to prevent ground loops. So I hope that makes sense. I'm not going to delve into ground loops too much, but in this application, in this example, you would ground the shield to the case of the transceiver, and then the end that goes to the connector where you plug in your headset, you would float that shield, put a little piece of heat shrink over it so that it doesn't accidentally short out to something if there's a strand or two peeking out, and that's how you would do that. Now you may be going through a couple connectors before you get where you're going. You want to continue the shield through the connectors, in one side and out the other. The way you do that is as I show here. We're going to take that shield and we're going to transition to a conductor from the braid. We can then crimp a pin on the conductor, go through the connector, reverse the process, come out the other side with an individual conductor with a pin on it or a contact, and then we're going to transition from that conductor back into the shield and continue the shield on out the other side. Now I'm going to show you how to bring the braid out as a pigtail so that you can crimp a contact on it and run it into a connector.
Then you do the same thing on the other side. The net result is the shield continues through a pair of connectors in one side and out the other. This is STP, typical 22 gauge shielded twisted pair. And what I've done, first of all, is I've scored the outer jacket right here, wiggled it around till it came loose, it broke loose, and then I slit all the way down this way and peeled that outer jacket off. So now I've exposed the braid on the inside. Then what you do is grab the braid back here somewhere and push it this way, and it's going to bulge in this area where it runs into the edge of the outer jacket. Then all you've got to do is go around and go snip, 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 cut the part of the bulge that's sticking out loose with your dikes, and you'll cut that braid off, and then you can slide that all the way off. You'll end up with a few stray strands that are sticking out. Trim those off with your dikes so that at that point, now the braid is cut off flush with the end of the jacket right here. And that part's fairly simple. When you're scoring the outer jacket here to remove this part, you'll be cutting through the jacket, if you push hard enough, into the braid. And the braid, at least with this type of fairly robust, sturdy braid, will protect you from scoring the insulation on the inner conductors. That's very important. With the really neat Sikorsky shielded twisted pair that I'm going to show you later, the braid is much more delicate, and you cannot depend on that to protect you. So you've got to be very careful to just score the outer jacket just enough so you can wiggle it, cause it to pop loose, and then pull it off. So now here we are, we're flush down here. We've trimmed off the braid, flush with the outer jacket. Now go up about a 1/4 inch. Very carefully, again, score the outer jacket all the way around. Wiggle it back and forth a few times till it pops loose, and then slide that off. Now you're going to end up with what you see here. You're going to have a braid that extends about a 1/4 inch out the end of the outer jacket. And now we're ready to use a nifty solder preform, which is called a shield terminator. And it's made by Raychem. I'll show you another cheaper way to do this, but this is my favorite way. This is how you do it in industry and aerospace. This little guy has 3 basic parts. Of course, there's a piece of high temperature heat shrink, clear shrink tube over the whole thing. Then you see on either side, you have these little blue bands. And in the middle is the solder preform. And soldered to that is a pre-tinned pigtail, this green number 22 wire. And all this stuff is Teflon insulation, so when you heat this up, it's not going to melt. This won't work with PVC because the PVC will start to melt when you hit it with a heat gun. So what we're going to do now, line that up so that the preform is right over the middle of the exposed braid, and then just hit it with a heat gun. Make sure nothing's moving while you do this, although it's going to take steps to prevent movement. What's going to happen is, of course, the heat shrink is going to start shrinking down. These 2 little blue bands are going to contract, and they're going to grab the outer jacket here and all of the wiring over here. And so that basically clamps everything into position so it doesn't slide around. The last thing to melt is going to be the solder inside of the heat shrink tubing. So believe it or not, this tubing gets hot enough to melt solder without it being damaged. Pretty tough stuff. So in short order, you'll see this start to melt. It has just enough solder in it to completely tin the braid and solder this pigtail onto the braid. So when you're done, this is all shrunk down, and the green pigtail is now the continuation of your shield. You can now cut it to length, crimp a pin on it. You can put it into a connector and then do the same thing on the other side. Bring a pigtail out the other side on the mating contact, transition back to braid, and away you go. So the shield is continued right through one side of the connector and out the other side of the mating connector. So that's how you do it. Now, if you don't want to do it this way, if you want to save some money, all you've got to do is just tin that braid with your soldering iron. Use a little solder. If you're using the kind of cable that I'm suggesting, mill cable with Teflon or Tefcell insulation, the solder will melt before the insulation gets damaged. If you're using PVC, again, that's not going to work. PVC, don't use it on your Helicycle. It's no good. It can't handle the temperature, and it's just not very strong. So you can simply tin the pigtail. Could be any old scrap of wire that's 22 in this case to match the conductors. Tin the braid, solder the pigtail to the braid, slide a piece of heat shrink over it and shrink it down. It'll accomplish the exact same thing that I just showed you here, and you'll save some money. So you can go either way.
Here's an example of what these shield terminators look like in practice. Here's a bunch of them coming into the back of a D-sub connector. And so you can see that the blue rings have clamped down around the wiring. The heat shrink has shrunk, and the solder preform in the middle has just enough solder to completely tin the braid and solder the pigtail onto the braid. So that's what those look like. They're very slick, but they're expensive. They're something like $1.50 a piece. So again, you can do the same thing by simply soldering the pigtail onto the braid and then put a piece of shrink tube over it and save yourself some money.
Here's two different types of 22 gauge shielded twisted pair. The one on the bottom is the more traditional 27-500 cable with typical braided shield that is very common. It's tin-plated copper made out of round strands. The one on the top, as you can see, is a lot thinner. The diameter is thinner because the insulation is thinner and the braid is thinner. It's very, very light compared to the one on the bottom. It probably weighs about half as much for the same length. And the interesting thing is the braid is made out of flat tape. See if I can undo a little bit and you can see. See that? It's more like a foil. It's more delicate, it's more difficult to work with, but if you're concerned about weight, this stuff is feather light. It's made to a Sikorsky aircraft part number. I bought this whole reel that I'm going to show you in a minute, so I have plenty of it. If you guys are interested, let me know. The conductors are silver-plated copper, and the insulation in the outer jacket is cross-linked Tefcell. So both of these cables comply with WC 27-500 standards, but I'd say the one on the top is a more sophisticated cable. But it's a little more difficult to work with because when you're trying to slice the insulation, the outer jacket, to install one of these shield pigtails, that braid on the bottom is a little bit tougher. If you nick the those little foil strips that make up the shield on the Sikorsky cable, you'll cut them and you'll have to start over. You just dike off the end and try again. But you can see that I did it here. None of the strands fell off. I'll move the camera a little bit. Maybe you can get a better idea of the relative size here. Can you see that? There's quite a big difference. So if you're interested in the Sikorsky shielded twisted pair, it's 22 gauge. So it's good, I would say, for anything inside the cabin or under the seat pan, anything that's not exposed to airstream and flight. And I only say that because 22 gauge is fairly thin wire. So I'm using 20 gauge for anything that's critical. I may use this for, say, for the strobe position nav light on the tail, and maybe some of the sensors. So, you know, if something came loose, it's not going to cause the engine to conk out. But for the critical to flight wiring, I'm going to go with 20 gauge. Or in a couple cases, I'm using 18. I'm running 18 back to the governor power just to keep the voltage drop down. I've never done that before, but I decided to on the helicopter I'm working on now. So these are two flavors of 22 gauge shielded twisted pair. One of them is more traditional on the bottom. The top one is custom cable made to Sikorsky aircraft standards. I've got probably 1,600 feet of this cable left, so if you're interested, drop me a note and let me know. And I'll sell it to you for half of what you're going to find this stuff for anywhere else.
Here's a shot of the cable that I'm selling. Again, it's 22 gauge, silver plated copper. The outer jacket is cross-linked Tefzel. It's very, very thin and extremely light compared to the cable of the same size that that has a traditional braid shield around it. So it's about half the diameter and probably half the weight for the same length, maybe less. This stuff is feather light. As you can see, I have a huge reel of this. I probably got 1,600 feet left, and I will sell you however much you want for 20 cents a foot. There's the description at the top. There is no 27500 part number for this cable because it has a Sikorsky aircraft part number, but it conforms to 27500 specs. But it's custom cable for Sikorsky. And my thought was, if it's good enough for Sikorsky helicopters, it's probably good enough for a Helicycle. So if you're interested, drop me a line, and I will unroll some of this and send it off to you. So that's it for this one. I've just kind of touched on this stuff. Wiring is a pretty complicated subject, so I hope this is of use. Here again you can see a couple of these D-sub connectors with the shield terminators on the back. In my next one, I think that'll be the last of this little series, I'm going to show you a bunch of aerospace connectors, going from really expensive down to the stuff that I'm currently using, which are not aerospace at all, but I think they're suitable for our application. If you have any questions or comments, drop me a line. There's my website, www.helicycles.org. You can reach me at Juan, Juan, at helicycles.org. So thanks for watching, and I will work on the next one and get that out as soon as I can.